Hello everyone, welcome to this lecture. So, in this lecture we will continue our discussion with perfectly secure VSS with n greater than 40, which we had discussed in the last lecture, and we will present a polynomial time protocol. So, I do not know whether you have noticed it or not, the protocol that we had discussed in the previous lecture, it was an exponential time protocol. Why it is an exponential time protocol? Because the set of happy parties is said to be the parties or the nodes representing the parties in the maximum size clique in the graph. Okay. And finding the maximum size clique, or basically checking whether there exists a clique of size at least n minus t, we do not know whether we have a polynomial time algorithm for that problem or not. Okay. We only have exponential time protocol. So, even though we have a nice protocol, its running time is exponential, we would like to make the running time of the protocol polynomial time, and we can do that. And the idea behind this polynomial time protocol will be to define the set of happy parties based on some other structure in the consistency graph rather than the maximum size clique. And what we are going to do is that alternate structure in the consistency graph will be the NT star, which we had used earlier in some other context. So, let me quickly recall the definition of NT star. So, if you are given a graph with n nodes, then an NT star basically consists of two subsets C and D, where the size of C is at least n minus 2t. That means, there should be at least n minus 2t nodes in the C set, there should be at least n minus t nodes in the D set, and C set should be a subset of D set, and there should be an edge between every node in C and every node in D. However, that does not mean that the nodes in D constitute a clique. However, the nodes in C constitute a clique. And we have also seen an algorithm which can help us to find an NT star in the graph, and that algorithm has the property that if it is guaranteed that my graph has a clique of at least n minus t, then the algorithm will definitely output an NT star. Well, it can output an NT star even if the graph does not have a clique, but what we are guaranteed is that if the graph has a clique of size at least n minus t, then the output of the algorithm will always be will be some NT star. Now, let us see that how we can find the set of happy parties based on NT star in the consistency graph. Okay. So, the protocol steps remain more or less same. The round 1, the dealer will distribute the row and column polynomials. In the round 2, the parties exchange the common points. Again, I am explaining the protocol without applying the round reducing technique, but at the end we can see that by applying the round reducing technique, the resultant polynomial time protocol can be reduced to 2 rounds. Okay. So, during the second round, the parties exchange the common points on their respective row and column polynomials over the private channels, and during the third round they make the result public based on the publicly available results of the pairwise consistency tests. The parties construct a consistency graph, and now we do not define the set of happy parties to be the parties representing the maximum sized clique. We do not do that, but rather what we do is we check whether some NT star is present in the graph or not. Okay. And how we can check this? We use the previous algorithm, the algorithm which we have for finding the NT star in the graph. We use that algorithm and check whether there exists some NT star in the graph, and if that algorithm outputs an NT star, namely a C component and D component, then the happy parties is said to be the parties representing the nodes in the D component of the star, and the unhappy parties will be the remaining parties. Okay. And the sanity check will be now that if the star algorithm fails to identify any star in the graph, then we can safely conclude that the dealer is corrupt. So, it is safe to discard the dealer. Now, let us see the properties of this modified protocol. The first claim is that if the dealer is honest, it will never get discarded, and the proof is very simple. If the dealer is honest, then there will be at least n minus t honest parties in the system, and since the dealer is honest, it will distribute pairwise consistent polynomials to all the honest parties. In fact, it is distributing pairwise consistent polynomials to all the parties, and these honest parties, when they perform the pairwise consistency check, they will come to know that the pairwise consistency checks are positive, and as a result every pair of honest parties P I P j will broadcast an OK message. That means, they will constitute a clique in the consistency graph, and the size of the clique will be at least n minus t. And now, we can use the property of the star finding algorithm, which guarantees that if there is a clique of size at least n minus t, then the output will be some n t star. And since for an honest dealer a clique is guaranteed in the consistency graph, it implies that an n t star is also guaranteed, and as a result the sanity check will fail, and hence an honest dealer will never get discarded. Now, the second property which we can claim with respect to this modified protocol is the following. Suppose the dealer is not discarded, that means some star is obtained, then the polynomials of all the honest parties in the D component of the star, they together lie on a unique t degree bivariate polynomial f star, where this f star bivariate polynomial is the f polynomial, f bivariate polynomial selected by the honest dealer. Now, why this claim is correct? So, since a star is obtained, what will be the cardinality of the C component of the star? The cardinality of the C component of the star will be at least n minus 2t, and n minus 2t means at least 2t plus 1, because we are working with the condition n greater than 4t. That means, there are at least 2t plus 1 parties in the C component of the star. Among those 2t plus 1 parties, up to t could be corrupt. That means, there are at least t plus 1 honest parties in the C component of the star. And remember, the C component of the star constitute a clique. That means, there are at least t plus 1 honest parties in the C which constitute a clique. That means, they have broadcasted an OK message for each other. That means, what we can conclude is the following: there are at least t plus 1 honest parties in C, and for every pair of honest parties P I P j in the C component of the star, their respective polynomials are pairwise consistent, because that is why they have broadcasted OK message for each other, and that is why they are part of the clique. And now, we can apply the pairwise consistency lemma, because now we have at least t plus 1 pairs of row and column polynomials guaranteed in the system which are pairwise consistent, and as a result we can conclude that the row and column polynomials of all the honest parties in the C component of the star together lie on this t degree bivariate polynomial f star. But that is not the claim. The claim statement is that the column polynomial of all the honest parties in the D component lie on f star. So, what we have proved till now, what we have concluded till now, that if we take the honest parties in the C component, their polynomials are lying on f star, but there might be some parties who are part of D, but not part of C. So, now let us prove the actual claim. So, consider any arbitrary honest party who is a part of the D component of the star. Now, what is the property of the star? The property of the star is that the node representing this party P I, it has an edge with all the parties representing the C component of the star. And when I say all the parties representing the C component of the star, that means both the honest parties in C as well as the corrupt parties in C. Forget about the corrupt parties in C. What we know is that definitely this honest party P I, who is part of the D component of the star, it has an edge with all the honest parties in the C component of the star, because Pi would have said broadcasted an OK message for Pj and Pj would have broadcasted an OK message for Pi. Okay. So, it has an edge with all the honest parties Pj in C. That means, if I take every honest Pj in the C component of the star, the column polynomial of Pj, yes, so the column polynomial of Pi and the row polynomial of Pi, they are pairwise consistent with the row and column polynomials of the honest parties Pj in the C component of the star. But the polynomials of the honest parties in the C component of the star, they lie on f star of x y. Because of that, we get this equalities, we get these two equalities, and how many such equalities are there? At least t plus 1, because we have at least t plus 1 honest parties guaranteed in the C component of the star. So, that means what we have shown here is the following: we have the row and column polynomial of the party Pi. There are for the row and column polynomial of Pi, there are t plus 1 points which also lie on the supposedly ith row and ith column polynomial of f star bivariate polynomial. And we know that two different t degree polynomials cannot have t plus 1 or more number of common points. That automatically shows that the row and column polynomials of the party Pi which it has received from the dealer, they are nothing but the supposedly ith row and ith column polynomial lying on this f star bivariate polynomial, which is defined by the honest parties in the C component of the star. And it is also easy to see that if the dealer is not on, if the dealer is honest, then this defined polynomial f star is nothing but the polynomial f of x y which has been selected by the dealer, because all the row and column polynomials which an honest dealer distributes are with respect to this bivariate polynomial f of x y. Okay. So, that is a main claim which we have proved, and now we can prove the correctness and the strong commitment property very easily for the modified protocol. So, let us call the bivariate polynomial f star evaluated at y equal to 0 to be the f star polynomial. It is going to be a t degree univariate polynomial in x. We consider it to be a summary sharing polynomial, and let us focus on the constant term of this defined f star polynomial. For an honest dealer, because of this claim statement, we automatically get that this defined summary sharing polynomial is the f of x polynomial picked by the honest dealer, and defined secret S star is nothing but the dealer's secret. Now, what we are claiming is here is the following: every honest party in the protocol outputs the ith point on this defined summary sharing polynomial, and again it depends upon whether the party Pi, that arbitrary honest party Pi, is part of the happy set or not. If it is a part of the happy set, then basically its share is nothing but the constant term of its column polynomial which it has received from the dealer, and we have already proved in the previous claim that the constant term of its column polynomial is nothing but the value of the f star polynomial at x equal to alpha I, whereas there is a possibility that the arbitrary honest party Pi is not a part of the happy set, in which case it recomputes its column polynomial, and again we can show that the recomputed polynomial is same as the ith column polynomial of f star bivariate polynomial. This is because the recomputed polynomial is obtained by applying the Reed-Solomon error correction process. Its degree is t, and the cardinality of the happy set of parties is at least 3t plus 1, with 2t plus 1 among them being honest parties. And now we can use the fact that the AGI values which are used by the party Pi on which the Reed-Solomon error correction is applied, they basically constitute points on this defined bivariate polynomial f star. Okay. So, because of the Reed-Solomon error correction property, because of the properties of the Reed-Solomon error correction, the recomputed polynomial g I of I is guaranteed to be the ith column polynomial of the defined bivariate polynomial f star. Okay. Now, that is the way we can make the protocol a polynomial time protocol, just by changing the structure in the consistency graph based on which the parties identify the set of happy parties. Now, this is a 3 round protocol. To make it a 2 round protocol, we can apply our usual round reducing technique, namely during the first round, apart from the distribution of the row and column polynomials by the dealer, every pair of parties can pre-exchange random OTP pads, and then during the second round the pairwise consistency check happens publicly through OTP encryptions, and then if there is a mismatch in the OTP encryptions, the edge between the corresponding parties is not added in the consistency graph, otherwise the edge is added. Then we check whether a star is present. If the star is not present, then we discard the dealer, otherwise we continue the protocol, and every party Pi who is not part of the happy set, it needs the AGI value to apply the Reed-Solomon error correction process for recomputing its column polynomial. The AGI values are obtained by unmasking the pads from the publicly available OTP encryptions. Okay. And the rest of the steps and analysis remains the same. So, this is the final 2 round polynomial time VSS scheme with n greater than 40, which is taken from this paper, and again for other perfectly secure VSS scheme you are referred to this survey paper. Thank you.